Hello everyone, welcome to the second part in the series on how to program a multicolored research-based Go-Plane program. So we continue from the previous part, and today we're going to be implementing routines to get the squares of a given group on a board and to get the liberties of that group. And this is very crucial functionality because this would help us to handle captures when it comes to making a move on board, and also for various evaluation purposes this would also be quite handy. But before going for that, let me fix a few things from the previous part. So the very first thing I would like to do is I want to rename the getSquare function to just square. Okay, and I hope it would still work. Okay. Then there is a bit of a problem. So if I do no code being specialized, it just prints this gibberish. I want to print empty instead. So let's quickly do that as well. So when it comes to co, I just do get rid of this for now, and I say if board co is equal to 0. In this case, I want to say fmt.print and empty, and otherwise I want to say fmt print and board.square. We'll just rename this, and board.co. Finally, want to print 2 new lines. So let's have a look. Okay, we got empty now, and if we drop back to this kind of thing, yeah, we got either the co-square, or if there is nothing, then we have like co is empty, like no co. Okay, now we can finally go for our routines. So I define a function. This would be board pointer to the board struct. So this is another part of another function being grouped to the board. So we can call it like board dot, and we call it count. So this function would be counting liberties, counting stones in a group, right? And it takes the square, it takes the color, both type integer. So let's define the stone as board position indexed by the square. So if it happens that stone is greater than 0, which means it's not an empty square, and also stone of a given color, so stone bitwise end with color is greater than 0, and also stone bitwise end with marker is equal to 0. So we need to make sure that this is not a marked stone. So the idea that we would be recursively crawling through all the 4 directions, north, south, west, and east. And once we hit a stone, we mark the stone. So this is what we're supposed to be doing over in here. So I say board position and indexed by the square. We want to mark with the marker. Okay, then we want to say board group equals to append, and we append to board group, we append the square, and I want to recursively call the count in all the 4 directions. So this would be square plus 1, and the color, and square minus 1, and square plus board size going downwards, and square minus board size going upwards. Okay. And other scenario, else if stone is equal to empty. So if this is an empty square, we just found a liberty. So we want to say board position indexed by the square to be bitwise odd with the liberty. And also want to say board liberties equals to append and board liberties and the square. Let's have a look if this compiles. Okay, it does compile indeed. Yeah, let's probably try to test this first. So I want to add some stones on board. So I say board position and 100 is equal to black. A couple more, so 101, 121. Let's have a look. Yeah, we got a group here. Great. So now we want to say board.count, and we want to count for square 100s. The result will be the same for square 101 and 122, but we don't care about this for now. So we just call the count, and then again board.show. The board structure would be changed, so we'll need to create a restore board function to essentially restore the board. But at the moment, okay, and count 110 for black. Yeah, the color would be black. Okay, so it prints nothing because we need to slightly alter the print board function that we have. So we may also have case black, and this is bitwise odd with a marker, and in this case fmt print, and I use the hash symbol. So this is the marked square, the marked stone within the group. And also I want the same for white. So if white is bitwise odd with a marker, also I want this. And also for liberty, so case liberty, I want this to be plus. Let's have a look. Yeah, now this is much better. So all those stones that has been counted are now turned into hash symbols, and all the liberties the group have turn into plus character. So now we know that we have all this stuff. Also, we want to add some additional information to our print board. So for instance, yeah, I can do this here, I guess. So fmt dot print, and I want to print group. Yeah, just group like this, and this would be a board group, and we want to have the new line, and also liberties and board liberties fmt. Okay, yeah, we got the group and we got the liberties. Let's adjust the indentation a bit. 3, 4. Yeah, and also after we can probably do something like fmt print like this. Okay, so we got the group. So our stones that we've done here. So stone 100, 101, 121. And these are the square indices for all the liberties we have. Great. So now the next thing to consider, we need to make sure that we can restore the board state. And we would be doing this in pair all the time. So let's create a function to restore the board. So same board, pointer to board, and call restore. And no, it's not taking any arguments. Restore does not take any arguments. So we do say board group equals to empty slice. So we essentially reinitialize the slice. Same for board liberties. Okay, equals to an empty slice, reinitializing it to no elements. And then we need to loop over all of the board squares. So square is equal to 0, square is less than board size multiplied by board size, and square is less than, yeah, it's not really good from the perspective of performance of these multiplications, but that's the price that we pay for having an opportunity to have the dynamic sizes for boards. So for now, this is just okay. We may rethink this later, but for now, this is just okay. And square plus plus here. And if board position square is not equal to of board, in this case, we want to restore the board position. So board position, and now index by the square. You remember that I told you that we can strip bits for markers and for liberties by simply bitwise ending with 3. So this is quite nice. Okay, and I think this is just good enough to restore the board. So board restore, and then again board dot show. Okay, let's have a look. Yeah, so starting from here, so we have the initial board. Okay, then first we don't have neither groups, no liberties being populated. Then we do the count. Okay, and now a group is populated with these 3 squares. Liberties is populated with 1, 2, 3, 4, 5, 6, 7 squares. 1, 2, 3, 4, 5, 6, 7 squares. Yeah, and then we restore things. After restore, black stones become black stones. White stones become there are no white stones. Liberties become empty squares. Okay, so one last thing to check here is that we can replace this black with white, and here this should be fairly similar result. Okay, so we have white squares here. Okay, and we have liberties, and now we have again like restored board position. So yeah guys, that's it from my side. Thanks for watching, and starting from the next video, we'll probably go and interact the routine to make a move on board. That would be quite a big routine, but that's the core behind the rows implementation. So after we do that, when it comes to the position where a group has no liberties, it would be erased, which means that those stones has been captured. So yeah, that's it from my side. Thanks for watching. I'll see you in the next video. Till then, and cheers.